All right, and welcome back. In this video, we are going to be going through Chapter 9, Section 2, titled Tangents. And by the end of this video, we should be able to apply theorems that relate tangents and radii, as well as recognize circumscribed polygons and inscribed circles. So let's have out our guided notes. Let's begin. So if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So if line AB is tangent to circle Z at point Y, then line AB is going to be perpendicular to segment ZY. If a line in the plane of a circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. So now we're talking in reverse order here. So if we know that line AB is in the plane of circle Z, and line AB is perpendicular to segment ZY at point Y, then we're going to know that line AB is tangent to circle Z. And likewise, tangents to a circle form a point that are congruent. So if segment AB and segment AC are tangent to circle D at point B and C, respectively, then we're also going to know that segment AB is going to be congruent to segment AC. Because notice that they're both segments are starting at point A, and that's what's in common. So we're starting at point A, and we go to the same circle, and we have a point of tangency at point B and point C, then we're going to know that we have congruent segments. And here's an example. If line RS is tangent to circle P at point R, we are given that PR, its length is 5, and RS, its length is 12. Well, we are asked to find the length of PS. Well, looking at this, we know that segment PR and segment RS, those are going to be perpendicular. So we're going to have a triangle. We have a right triangle, and we can use the Pythagorean theorem. So we're going to know that PS squared is equal to PR squared plus RS squared. And as we simplify it down, we figure out that PS is going to be 13 by using the Pythagorean theorem, which is pretty cool. It's kind of full circle. All right, please work on problems 1 through 8 on the guided notes and resume when you're ready to move forward. We also have some more applications of these tangents. We have what's called a common tangent. A common tangent is a line that is tangent to each of two coplanar circles. That's what's going to be a common tangent. So if you look at the diagram over on the right-hand side, we have one line intersecting both circles and in the same general vicinity. If we had this circle on the left-hand side, the common tangent is going to be hitting at the top, and then we have a common tangent hitting at the top again. But that's going to be specifically a common external tangent. So if we jump down to the second bolded statement, because I definitely went out of order here, a common external tangent does not intersect a segment joining the centers of the circle. So what I was saying before is that if we have two circles and they're in like more or less a corresponding area of those circles, and it does not cross the centers, that's going to be a common external tangent. And likewise, we have a common internal tangent, which will cross the two circles. So it kind of looks more like alternate interior angles, but not really because we're talking about a circle. But that's kind of the diagram. The common internal is going to go through the middle of those two circles, internal inside those two circles, while the common external tangent is going to be on the outside, external. So a common internal tangent intersects the segments joining the centers of the circles. That segment joining the circles is imaginary for right now. We don't actually have to draw it every single time, but if we imagine one segment coming through the two centers of our circles, then we can differentiate between a common internal, which is going to cross over that line, or a common external, which will not cross over that line. And we also have what's called tangent circles. So two coplanar circles that are tangent to the same line at the same point are tangent circles. And two tangent circles are internally tangent or externally tangent. So we have this other diagram over on the right hand side, and we're going to focus in on this first piece that looks more to the left. These are internally tangent circles. We have two circles that are tangent at the exact same point, which is going to be where my cursor is. They're hitting that line at that one point, and one circle is inside of the other. But now we have what's called externally tangent circles, which is going to be this circle on the right hand side and the bigger circle on the left-hand side. They're on opposite sides of that tangent line. So they're going to be externally tangent. If they're on the same side of our tangent line and one of the circles is inside the other, is going to be internally tangent circles. If we have two circles on opposite sides of a tangent line, they are going to be externally tangent circles. And lastly, we have the opposite of what we learned about last video. We have what's called a circumscribed polygon and an inscribed circle. So a polygon is circumscribed about a circle if each of its sides is tangent to the circle. And likewise, a circle is inscribed in a polygon and each of the sides of the polygon is tangent to the circle. So this time we have a polygon on the outside of our circle and the circle is inside of that polygon. Now, all the sides of our polygon are going to be tangent to the circle. So we have 4 points of tangency about that circle. With this in mind, please work on problems 9 through 17 on the guided notes. Keep up the great work. Keep making yourself proud. Let us know if you have any questions, and we'll talk to you soon.